In previous videos, we applied the Laplace transform method to solve linear dynamic equations. And we also used the state space method to rewrite a linear, multidimensional dynamic system into a single matrix equation. Here we will look at the blending process, and we will combine Laplace transform and state space. Let's start out and write out the general form for a state space model. We have dx dt, our time derivative terms that usually come from accumulation terms in a balance equation. That equals ax plus bu, and then we have our measurement equation, y equals cx plus du, and that's just algebraic, not differential. So these are linear equations, and we can take the Laplace transform to get s, x of s, minus x of 0, that's the Laplace transform of the time derivative dx dt, and that equals a x of s plus b u of s, where u are our process inputs, either the manipulated variables or the disturbance variables. Here w1 is disturbance variable, and we'll use w2 as our manipulated variable. Then we can also take the Laplace transform of our measurement equation to get y of s equals c x of s plus d u of s. And when we take the Laplace transform of a function of t, we usually change the lowercase variable to uppercase to denote that it's in the Laplace domain. Now we will go ahead and we will solve our first equation for x of s. So x of s appears on both the left and right hand sides. So we will combine our terms that have x of s here and put all of our other terms on the right hand side. So this all works pretty much the same as it does with scalar equations when we have matrix equations, but we do need to be careful and remember that we're dealing with matrices. So we had to multiply our s by the identity matrix so that it would have the right dimensions to then have a subtracted from it. But now we can go ahead and we can solve for x of s. Again, we need to remember that we're dealing with matrix equation, so we can't just divide by si minus a. We need to take the matrix inverse. And now we can look at our measurements, y of s, and we can plug in x of s. And finally, we may wish to recombine some terms so that we have a single coefficient multiplying u of s. The term that multiplies our input u and describes its input on the measurement y is sometimes called the process transfer function. Now that we have the numerical values for a, b, c, and d for the blending process, we can go ahead and calculate the process transfer function. So if we look back at our y of s equation up at the top of the screen, we have two terms, one for the initial condition. In this example, we will assume that we start off with 0 deviation. So we can focus on the second term. And if we want to calculate g of s, the first thing we need to do is to calculate si minus a, which is s, 0, 0, and s plus 4 times 10 to the minus 4. Then we need to invert that, and in general, that would not be so trivial, but because it's a diagonal matrix, here we can just take the inverse of the diagonal elements. If it wasn't diagonal, then you could use something like Cramer's rule to invert a 2x2 matrix. But now let's go ahead and calculate our transfer function, g of s, which is c times si minus a inverse times b plus d. We can go ahead and multiply the three matrices c, si minus a inverse times b, and then we can add to it d. And when we do that, we get a 3x3 matrix. Now that we have the transfer function g, we have a mathematical expression for the relationship between our measurements and our inputs. So let's consider the step input of 0.1 to W1 prime of t, to our disturbance variable that we have considered in previous videos. So we'll have W1 prime of s is 0.1, the height of the step, over s, since the Laplace transform of the step input is 1 over s. So our input u, recall, was W1 prime, W2 prime, and W prime. So in the Laplace domain, that is u of s is 0.1 over s, our W1 term, and then we have 0 deviation in our other two inputs. In this example, we can write y of s as the product of g and s and u and s, and get 0.1 over s, 10 to the minus 4 over s squared, and 7.5 times 10 to the minus 7 over s times s plus 4 times 10 to the minus 4. Just by multiplying the matrix G of s, which is a 3 by 3 matrix, times the column vector U of s, which has 3 rows. Now that we've solved for y of s, we can take the inverse Laplace transform to solve for y of t. So the inverse Laplace transform of that step is just 0.1, the constant for t greater than 0. The Laplace transform for the second term, 10 to the minus 4 times t, that's the inverse Laplace transform of 1 over s squared. And finally, we have 7.5 times 10 to the minus 7 divided by 4 times 10 to the minus 4 times 1 minus e to the minus t times 4 times 10 to the minus 4. In an earlier video, we wrote this as t over 2500 and viewed that as the time constant. So either one is equally applicable. But here we've gotten the solution for all three of our measurements. W1, the disturbance variable, as well as the volume in the tank and the mass fraction of the tank in deviation variables. And we've done that using a single matrix equation.